Hello, I'm Carmine Abate from the Max Planck Institute for Security and Privacy. And today I'm going to talk to you about fully abstract and robust compilation and how to reconcile the two abstractly. This is a joint work with Matteo Busi and Stelios Tsampas. So first of all, let's try to understand what we expect from a secure compiler. A secure compiler should not introduce any bug that can break the security of source programs. In other words, secure compiler should preserve all the security properties of our source programs. So to make the intuition of secure compilation formal or rigorous, we need a formal definition of security. In the criterion called fully abstract compilation, security is modeled through, is expressed through indistinguishability with respect to an attacker. Attackers, in turn, are evaluation context, so that a compiler is required to preserve and reflect contextual equivalences. So we denote a compiler with bold bracket, and in symbols, a compiler is fully abstract if and only if whenever two source programs, P1 and P2, are equivalent in any source context, CS in blue, then after compilation in the target, P1 compiled and P2 compiled are equivalent in any target context, CT in red. This implication is called preservation, and the inverse implication is called reflection, and is sometimes subsumed by compiler correctness. So what we really care is preservation of contextual equivalence. Fully abstract compilation has been successfully used to show the preservation of confidentiality that can be quite easily modeled in terms of equivalences, but also to show the preservation of other interesting security properties, such as well-bracketed control flow or local state encapsulation. Fully abstract compilers have been defined for several scenarios, for example, to compile to modular architectures, but also to compare the expressiveness of two different languages. Okay, let's move now to the other criterion that is of interest for us. Robust compilation. In robust compilation, security is expressed with hyperproperties that are sets of execution traces. A compiler is said to be robust if it preserves the robust satisfaction of hyperproperties. In symbols, we require that if P satisfies a certain hyperproperty H robustly, meaning that it satisfies H in an arbitrary source context CS in blue, then in the target, P compiled satisfies the interpretation of the same hyperproperty but in the target, tau H, in an arbitrary target context, CT in blue. By picking the right classes of hyperproperties, the formula I displayed describe a compiler that preserves robustly the notions such as data integrity, data confidentiality of observational determinism. Okay, now that we have two distinct notions of secure compilation, then it's natural to ask ourselves, which one shall we choose? Is there one that is always better than the other? And to have a good answer, we believe that we should compare the guarantees that each one of them give on compiled programs. More precisely, assume that your source program enjoys some security guarantee. Then what can we say on P compiled? Will it have the same guarantees or some other sort of guarantee or no guarantee at all? Well, if your compiler is robust, then P compiled enjoys the very same guarantee because it will satisfy robustly the same hyperproperty expressed in the target. While the literature and also us gave examples of fully abstract compiler that don't preserve some security guarantee. For example, we focused on non-interference and defined a fully abstract compiler that does not preserve non-interference. Then what can we say about fully abstract compilers? Our first contribution consists in showing what is the exact hyperproperty that is robustly satisfied by p-compiled when the compiler is fully abstract. However, we argue that such hyperproperty is not at all easy to compute and can sometimes be trivial. For example, when the source hyperproperty is not preserved by the compiler. But then, what does this mean? That we should give up on fully abstract compilation and use only robust compilers? Well, no, because even if fully abstract compilers may not preserve all hyperproperties, they still preserve many of them. And moreover, it's very useful sometimes to express security through equivalences. For example, when there are no observables or there's no really a trace semantics for our languages. Finally, fully abstract compilation exists since 20 or more years. So there are many well-established proof techniques for it that are based on logical relations, back translations, and bisimulations. And these proof techniques sometimes can be adapted to also show that your compiler is robust. So ideally, we would like to have both these benefits of fully abstract compilation, but also an explicit description of the guarantees in the same way robust compilation gives us. And to do so, we adopt a slightly more abstract point of view. Okay, so our scenario can be simplified as following. We have a source language in blue, a target language in red, and a compiler from the source to the target. And the first thing we do is to give a formal description of the source language by providing a syntax functor and a behavior functor. You can imagine the syntax functor as the algebraic signature of your language. And we relate the syntax functor and the behavior functor with a distributive law that corresponds to a collection of rules that specify the operational semantics of the source language. We do the same for the target language. So we take the algebraic syntax functor and the behavior functor of the target language, and we specify the operational semantics by giving a distributive law between these two functors. Now, a compiler can be defined as a pair of maps. One that is a translation of the syntax functor into the syntax functor, and the other B that is a translation of behaviors. Stelios, in a previous work, proved that a notion of compatibility of these two mapping implies the preservation of bisimilarity. That in this setting means that your compiler is fully abstract. In particular, it is required that the B translation, so the translation of the behavior in the source of a source term, is compatible with the target behavior of a source translated term through S. However, in our paper, we show that, yes, you get a fully abstract compiler, but this compiler can still be not robust because not all target contexts are always taken into account. And so we had to make explicit how target context and source context can be defined in our language. And we picked a functor also for the context. And we require not only a translation of the source syntax functor into the target syntax functor and a translation of the behaviors, but also a mapping from target context to source context this time, that is called the back translation. And here we show that the notion of compatibility of S and B, together with the notion of compatibility of this back translation with B, provides both fully abstract and robust compilation. So to recap, in this paper, we compared fully abstract and robust compilation as secure compilation criteria. And as a first contribution, we showed what are the hyperproperties that are robustly satisfied, robustly preserved by fully abstract compilers. Then, since the answer was not fully satisfactory for us, we provided a novel criterion in a quite abstract setting that implies both fully abstract and robust compilation. In the paper, you can find way more. You can find an example of a fully abstract compiler that is not robust, because in particular, it does not preserve the robust satisfaction of non-interference. Then we show how such a compiler can be fixed, and so that it respects the criterion, the novel criterion we introduced, and can be both fully abstract and robust. Of course, you can find all the definitions and all the proofs in the paper or in the appendix, together with an introduction to all the categorical background that is needed to understand this work. I would like to mention that we might avoid this categorical machinery one day, because there is an exciting ongoing work that is targeting an ACDA mechanization that is progressing quite quickly thanks to Stelios. And that's all I have to say. Thanks for your attention. We are happy to take any question.